Programming Concepts and Methods 1, and we're going through this Python book, and we're up to Chapter 5. So let's take a look at, I want to get to Opera, and here we are, Chapter 5. So I go to the textbook. If you scroll down a bit, here are the notebooks, the Colab notebooks. So I run this one just to get it ready, and it warns me that it's not written by Google, so it could contain nasty code, but I'm running it in a sandboxed environment in the cloud on Google servers with a throwaway account. So I'm pretty safe even if it was to have some kind of nastiness in it, which I don't think it does. And so we're going to talk about conditionals and recursion. The first thing is a little bit of math. So if I have minutes, it's 105, and then I divide it by 60 with a single slash, that division will turn it into a floating point number, 1.75. 105 is an integer and 60 is an integer, but dividing makes it 1.75. You can do integer division with two slashes, and what that will do is round down, it'll truncate it. So 1.75 becomes 1, and it's an integer. Now if you wanted the remainder, which is 0.75 times 60 or 45, you could subtract off 1 hour's worth of minutes and get the 45 minutes. Or you can use the modulus operator, which is quite powerful and used a lot, especially in cryptography. Modulus divides minutes. This midget's modulus 60 will divide by 60 and print the remainder, which will always be a number between 0 and 59. So it takes away all the integral multiples of 60 and prints what's left over, which is 45. So for example, if you take 123 and take it modulus 10, you'll get just the last digit. And if you take it modulus 100, you'll get the last two digits, because you take away all the multiples of 10, that leaves you only the last digit. Take away all the multiples of 100, that just takes away the 100 and leaves you the 23. So these turn out to be pretty useful. And another thing you can do is clock arithmetic, which is what you do in cryptography. You do modular arithmetic. Instead of having numbers that go from 0 to infinity, you just go around a loop up to a certain size and then around and around a loop, so you have a limited range of outputs. And so here, for example, if you go around a clock, event starts at 11 a.m. and goes 3 hours. Then you start at 11, 3 more hours, you add them together, and then take modulus 12. So you get 2. 11 a.m. going for 3 hours, you end up at 2. That's the kind of thing. All right, because the numbers always go between 0 and 11. And that's a way to represent a clock, although you normally call 0 12, but in modular arithmetic, you start at 0. So then there are Boolean expressions, which are either true or false. Two equal signs says something's equal, so 5 equals 5, that's true. 5 equals 7 is false. It is very common that people make a mistake and use a single equal sign. So instead of comparing x to 5, this assigns 5 to x and puts 7 in y. So now x equal y is false. But it's quite common that people use a single equal sign when they mean a double. It's a common error people make. All right. And true and false are Boolean strings, Boolean values. Type is Boolean. Boole is a mathematician that developed this kind of math where you have bits, things that are 1 or 0 or true or false. So you have other ones like not equal, greater than, less than, greater than or equal, less than or equal. They're all pretty obvious. And then you have logical operators to make compound conditionals. So here, if x is greater than 0 and x is less than 10, then that will be true. And I wonder what x is. I've forgotten. Let's find out what x is. All right, x is 5. Okay, so, all right. And so it is true. If it's 5, it's between 0 and 10. So this expression is true if either condition is true. So if x percent 2 is 0, which is false, because x percent 2 will take 5 and remove all the even multiples of 2, which is 4, and there'll be 1 left. X percent 3 is also not 0. The answer is 2. You take away 3 and there's 2 left over. So both of these conditions are false. So the end result is it's still false. If either one of them is true, though, then it would be true. So if I made this not equal to 0, then this one is true and that one is false, and now the combined condition is true. Because if either one of them is true, the combined condition is true if you're using an OR. If you have an AND, they both have to be true to make the compound conditional true. And then there's not. So if x is greater than y, not greater than y is just the opposite. So if x is greater than y is false, not x greater than y is true. All right. And Python is not very strict, so you can use a number and it'll be treated as true. So 42 is interpreted as true, and true is true, so the combination is still true. All right. That can be kind of annoying. Python uses this loose typing, which can get you in trouble. You can refer to things and it's not entirely clear what variable type it is, and it sort of guesses. So does JavaScript. And in fact, I have a fun video talking about the concept, some of the trouble you can get into with loose typing languages. I'll show you later. Anyway, so if statements. You need the ability to check conditions and change the behavior of the program. So if x is greater than 0, print something. So it'll do that. You have the colon, you have indentation, and so it'll only do this if x is greater than 0. If I make it if x equals 0 with 2 equals, then it won't print anything because that condition is no longer true. All right. So if x is less than 0, then pass, which will do nothing but just move on. And so if in this case, it'll never print anything. There's no print statement anywhere. I'd have to add something below this for it to do. And then there's an else clause. If x%2 is 0, print it's even, else print x is odd. This is very commonly done when we have two possibilities. Some condition is true if it's false, else is what happens if this condition is not true. So x is odd because it's 5. All right. And you can have change conditionals with elif. If this condition is true, it prints that. Else, if this condition is true, it prints that. Else, if everything so far has been false, then it prints this. And you can have as long a chain of these things as you want. So here we have 3 conditions: x is less, x is greater, and x and y are equal. And in our case, x is less than y. All right. And you don't need to have the else clause. You can just have if, elif, and then it'll only act on the first one it finds that is true, and the others will just do nothing. You can also have nested conditionals, or if x equals y, print this, else. Here we know x does not equal y. Now we indent to the same level. So this condition is this is the opposite of this condition because it's the else. So we know x does not equal y. So in here we have another test to separate less than and greater than. That's another way to do it. All right. And all right. And then you've got logical operators here. So if x is greater than 0, 0 less than x, if x is less than 10, then print this. It's a positive single-digit number. All right. You can do this with 2 if statements indented, or you can do it with one compound conditional. 0, x is greater than 0, and x is less than 10. You can do it this way, or you can do it that way. They both have the same result. And there is a more concise option. If you want to do this, you can have x between 0 and 10. Sort of easy to read, a special case. All right. So that's Boolean conditionals. And the next topic is very interesting, is recursion. And if you take the course after this, you do a lot of interesting recursion. So recursion is where a function calls itself. That might seem insane, but it is actually quite useful. So here we're going to have a countdown of n. If n is less than or equal to 0, then you print blast off and you're done. Otherwise, you print n and call countdown of n minus 1. So it will launch another instance of countdown and do this and another, and each one will have its own stack frame. You can have many copies of the same function running. They each have their own separate local variables, and it won't return until they're all done. So countdown of 3 will pass down here, it'll print 3, and then it'll call 2, 2 will print, 1 will print, and when you get to 0, it will say blast off. So this defines the function, and here's what happens when you count it for 3, you get 3, 2, 1, blast off. And so while this is running, it has 4 copies of this thing running in memory. It calls itself. Now, all right. And there's a nice diagram here showing the first one starts with 3, it launches a copy of 2, that launches a copy at 1, and that launches a copy at 0. So at this point you have 4 of them in memory, using memory, and then it starts returning from the wall. So, all right. You can call yourself recursive. Here's another one that will print a string n times, and what it does, it prints the string once and then calls itself at n minus 1. So again, if I say print spam 4 times, it'll print spam, 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 by exactly the same logic. All right. And you can look at a stack diagram to see the frames. They sort of like these in this chapter. Kind of obvious. It looks like this. You have a version to countdown with n of 3, and with n of 2, and with n of 1, and with n of 0. What's not obvious in this diagram is that there's a point in time when they're all running at once. All right. And let's see, you can make another diagram here. Yeah, which just shows the other one, string hello, printing hello, hello, hello. All right. And you might wonder what would happen if you made infinite recursion. You know, here we had a copy of this function run at n, and it called another one at n minus 1. And it had this condition that when n hits 0, it'll stop. So if you fouled that up, if you didn't have a condition to stop, or you failed to decrement this number every time, you might have an infinite loop that'll just keep calling itself over and over. And they have a nice example of that here. Recurse just calls itself, that's all it does. So you can define it, but when you run it, it's going to go forever. And so by using some of these extra flags, they make it so it'll print interesting information about the exception, and so it crashes. And they claim here that there were 3,000 frames on the stack when it crashed, although I can't see any number here that tells me that. I'm not sure how they determined that. For me, I would have modified the thing to print out a number every time, or something like that, and then show that. In fact, I wonder if I can do that. Let's try that. What happens if I'm going to try doing something. What happens if I take recurse of n, and then I call recurse of n minus 1, and before I call it, I'm going to say if, if n% 100 equals 0, then it's just an even 100, then I'm going to print n. There, print n. All right, and then I'm going to define it that way. Oh, yes, I didn't get a colon, I got a quote there, okay. I think that's right now. And now I'm going to call recurse of, say, 4,000 and see what happens. Oh, there we go. And you can see it started at 4,000 and it got down to 3,100. So in this case, it was not able to put 3,000 in memory before I ran out of memory here. It looks like it was only able to run about 1,000. So let's try starting it at 1,000. And in that case, it still crashes. So even 1,000 is more than you can fit apparently in memory. And if I make it bigger, like 2,000, yeah, I only get some of them. So I guess 900 should not crash. 900? Now it still crashes. That's why I'm not quite sure. Maximum recursion depth exceeded. That's why I don't quite understand what's going on here. I thought there would be a limit I could measure, and numbers below that limit would not crash. Oh, I see. I forgot to stop at 0. That's why. Let's put that in. If and n greater than 0. There. Let's try that. Then I'm actually limiting how many times it runs. And so here's 400. And 400 stop. Maximum recursion depth exceeded. That's right. I don't quite understand how you measure this recursion depth. I'm not going to keep struggling with it. Doesn't seem to be simple to say how many copies you can fit in memory. Anyway, all right. Then there's keyboard input, another useful thing to know. There's this function called input. So if I just put, if I just run this, it will ask for data. So if I put in data like hello, it'll take it. And so here I can have name as input with a prompt, and then it's going to print the prompt and ask me stuff, so I can now give it a name. If I can type it all. All right, there you go. All right. And so here I can have a prompt. It'll read this and then print it out, sort of thing. Now here it's looking for, now by the way, the input is always text. So if I wanted to print speed, I could print, well, first let me run this. So here, if I give it like 3, it prints 3. But it's a text 3. That's what the quotes mean. If I print, whoops, I used lowercase, print. I thought I hit lowercase, print. Print speed, and then I want to print type of speed. There. So now I run it, and I give it 3, and it is a string. It's not an integer. So if I wanted to add 1 to it or something, I'd have to turn it into an integer first. All right, and so here, but if I put in something that's not an integer, right here I'm going to calculate the integer. So if I was to run this and put in a non-integer, like Fred, then it'll work here, Fred class string, but when I try to make it an integer, it's going to fail. You can't turn Fred into an integer. So that's an issue of errors. All right, we've already talked about these possible expecting an error, so you can just print out, this one has an indentation error, and this one, numerator is 9, denominator is 5, ratio is numerator over denominator, decimal is 10 times math log 10 of ratio. There's a problem in line 4, they say. Not obviously, uses integer, oh, they're talking about this line, integer division instead of floating point division. So the ratio is an integer, and the math log probably can't run on integers. That's probably the issue. So yeah, that's the issue. The math domain here can't handle the ratio. If you used a normal division here, it would be floating point, and then it would work. All right, there's some examples of debugging there. All right, well, that's what I wanted to show you from the chapter. Let me stop this recording.